Tassiana, será melhor mandar alguma mensagem para todos, dizendo que está tendo algum probleminha?
Estou mandando, Clarice.
Tá. Ah, já?
Eu ainda não estou vendo, Eduardo.
Ainda não?
Ah, já vi.
Já viu?
Sim, gente, estamos ao vivo. Pode começar.
Podemos começar?
Podemos.
Então, vamos lá. Bom dia a todos. Good morning to our visitors. Good morning to our president of the IBS and to our RBras president. Inicialmente, agradeço aos docentes e funcionários do Departamento de Ciências Exatas, representado por seu chefe, Edwin Ortega, e ao Programa de Pós-Graduação em Estatística e Experimentação Agronômica, representado pelo seu coordenador, Idemauro Antônio Rodrigues de Lara, docentes e discentes. A organização dessa reunião só foi possível graças ao apoio de todos. Agradeço também aos membros da comissão organizadora e da comissão científica, que trabalharam para termos um programa científico de excelência para seus participantes. Agradeço a diretoria e conselho da RBras, e especialmente a todos os convidados que vão proferir palestras e lecionar minicursos, e também aos pesquisadores que submeteram seus trabalhos. O Departamento de Ciências Exatas, antigos Departamento de Matemática e Estatística, sempre participou ativamente da RBras, desde a sua fundação em 1955, na pessoa do professor Pimentel Gomes, e da idealização do SEAGRO nas pessoas dos professores Humberto de Campos e Décio Barbim. Os docentes de nosso departamento e programa de pós-graduação em Estatística e Experimentação Agronômica sempre se envolveram em cargos da região brasileira da Sociedade Internacional de Biometria e da própria International Biometric Society, e participaram tanto das reuniões nacionais como das internacionais, como tradição, além de incentivar a participação dos discentes. Infelizmente, desta vez, nossa reunião está sendo online, mas nós esperamos poder, num futuro muito próximo, recebê-los em nosso departamento presencialmente. Desejamos a todos uma profícua reunião nesses 2 dias. A seguir, nós convidamos o professor Paulo Canas Rodrigues, atual presidente da região brasileira da Sociedade Internacional de Biometria, para proferir suas palavras de bem-vindos à nossa reunião.
Excelentíssimo Sr. Geert Verbeke, presidente da Associação Internacional de Biometria, excelentíssima Senhora Professora Clarice Demétrio, coordenadora-geral da 65ª reunião anual da região brasileira da Sociedade Internacional de Biometria e do 19º Simpósio de Estatística Aplicada à experimentação agronómica e representante do Departamento de Ciências Exatas da ESALC USP. Membros do Conselho Diretor da RBras, prezados associados e congressistas, prezados colegas, senhoras e senhores, bom dia. É com grande alegria e satisfação que nos reunimos novamente, desta vez de forma online, em nossa tradicional reunião anual, envolvendo professores e pesquisadores com atividades no ensino, pesquisa e extensão na área de biometria no Brasil e no exterior. A região brasileira da Associação Internacional de Biometria foi fundada em 1955 e é uma das mais antigas associações científicas nacionais. É também uma das maiores regiões da Associação Internacional de Biometria, que contém mais de 6.000 membros e é composta por 37 regiões e 4 networks em todo o mundo. Eu vou agora partilhar aqui a minha tela para vos mostrar uns 5 slides que eu preparei sobre uma apresentação breve sobre RBras. Então, atualmente o Conselho Diretor da RBras, ele é composto por, ele tem presidente, vice-presidente, primeiro e segundo secretário, primeiro e segundo tesoureiro, além do presidente do biênio anterior, e 6 conselheiros, além dos membros do Representative Council, que são representantes no Conselho, representantes da região no Conselho da IBS. Então, agradecer também desde já a todos os colegas do Conselho Diretor pela prestação de serviços à RBras. Eu queria dar algumas notícias recentes. Uma das mais recentes é que a Revista Brasileira de Biometria passou oficialmente a ser a revista oficial da RBras. O editor-chefe é o Thales Fernandes, de Lavras, e tem como editor o Carlos Pereira, da Universidade de São Paulo, o João Scalone, da Universidade Federal de Lavras, e eu, da Universidade Federal da Bahia. O nosso website da revista é biometria.ufla.br, UFLA Federal de Lavras. Então, nós estamos aceitando o tempo todo os vossos trabalhos, então o nosso objetivo é que esta revista passe a ser alguma referência em termos nacionais na área de estatística aplicada e biometria, então, e com índices relevantes em termos internacionais. Então, os vossos trabalhos que vocês acham que são interessantes dentro da área, nós teremos todo o prazer em recebê-los. Em breve, nós vamos ter as eleições para 2021. Nos anos ímpares, nós elegemos 2 conselheiros. Então, em breve, provavelmente na próxima semana, vocês receberão um link dedicado vai ser um link para cada associado para a eleição. Não esqueçam que vamos ter a Assembleia Geral no dia 25 de setembro, às 13h45, em primeira convocação. E, além disso, nós estamos agora trabalhando no novo website da RBras. O atual, ele tem demasiados problemas e já tem um design um pouco antigo. Então, estamos a trabalhar num novo website. Então, nós estamos a pedir sugestões. Quem tiver alguma sugestão para enviar, pode enviar para mim por e-mail. E também nós queremos colocar algo mais pessoal, ou seja, colocar fotos de reuniões passadas. Então, especialmente quem tiver fotos relevantes, que acho relevantes, ou fotos de grupo de algum congresso anual passado, que me envie para nós podermos colocar no website. Em termos de benefícios, nós temos bastantes benefícios para os nossos associados. Como nós fazemos parte da IBS, então todos os benefícios da IBS são automaticamente facultados aos associados da RBras. Então temos acesso online aos jornais Biometrics e Jobs e ao Biometric Bulletin. A IBS organiza conferências a cada 2 anos, então é uma oportunidade extraordinária para poder interagir com pessoas e pesquisadores de todo o mundo. Ela tem mais de 6.000 membros, como eu falei mais cedo. Existe também, como o Brasil é um país em desenvolvimento, existem sempre umas travel grants, ou seja, umas bolsas financeiras para ajudar a pagar as despesas, para participar em eventos organizados pela IBS. Da mesma forma que cada região, cada uma das muitas regiões, também organiza eventos, então também associados da RBras têm também preços reduzidos de inscrição. Então tem todas essas vantagens. Além disso, nós temos agora, recentemente, também um grupo de jovens pesquisadores na RBras, então para os colegas mais jovens é algo que pode ser interessante para trocar ideias. Eles vão, inclusive, organizar uma sessão hoje pela tarde no Congresso. E, além disso, é sempre um prazer nós podermos reunir anualmente, infelizmente desta vez online, mas esperamos que no próximo ano já possa ser presencial novamente. Então, esta é uma parte dos benefícios dos associados. Para se associarem, basta ir ao website da RBras e escolher a filiação, e aí tem uma ficha de inscrição. Caso tenham alguma dúvida, podem contactar o nosso primeiro tesoureiro, é o professor Paulo Henrique Guimarães, da Universidade Federal de Lavras, através de tesourariaRBras@gmail.com. Então, isto é aquilo que eu queria falar um pouquinho sobre a RBras, para quem não está tão familiarizado. Na sequência, eu vou finalizar a minha intervenção agradecendo e parabenizando a comissão organizadora local, capitaneada pela professora Clarice Demétrio, por todo o empenho e dedicação que dispensaram para a organização da 65ª RBras e 19º SEAGRO, com atividades de altíssima qualidade. Agradecemos também a todos os colegas que integraram a comissão científica, em particular os seus coordenadores, professora Renata Sermarini e professor Silvio Zorri. Em nome do Conselho Diretor da RBras, também gostaria de agradecer a todos os conferencistas, os tutores dos minicursos que ocorrerão amanhã e apresentadores de comunicações orais. São vocês que prestigiam e abrilhantam o nosso evento, compartilhando connosco o vosso conhecimento e experiência. A vossa presença honra-nos imensamente e engrandece o nosso evento. A todos vocês, congressistas e participantes, gostaríamos de dizer que vocês são o propósito das nossas reuniões anuais. A RBras sente-se honrada com a presença de todos e vos recebe de braços abertos. Todo o trabalho da comissão organizadora e da diretoria da RBras e do Conselho Diretor foi no sentido de oferecer a vocês, participantes, um espaço adequado para troca de ideias, para a apresentação de resultados e tudo isso. Se ocorreu ou ocorrer alguma falha, saibam que foi involuntária. Now in English, a few words. I apologize for speaking all the time in Portuguese. On behalf of the Brazilian region of the International Biometric Society, the largest Brazilian association for applied statistics, I would like to welcome all of you to the 65th annual meeting of the Brazilian region and 19th SEAGRO, and wish you a fruitful meeting and enjoyable and good time. Assim, em nome da RBras, duas boas-vindas a todos e desejo-vos excelente congresso. I will now give the word to Geert Verbeke. He is the current president of the International Biometric Society, and he will tell us a few words about the IBS.
Okay, well, thank you very much, Paulo, for the introduction. Also, thank you for the invitation. It's really a pleasure for me to join you in this meeting. I had hoped to be able to attend your meeting last year live in Brazil, but of course that had to be cancelled. We all know what the reason is for that. But anyway, I'm still happy that I can join today. And I have prepared a few slides on IBS. Okay. Let's see if that works. So you should get to see. Can you see the screen?
Yes.
All right, good. I mean, when I was first attending a meeting of the Belgian region, I had no clue that there was something like IBS sitting on top of the Catalyst Society, which is the name of the Belgian region. And I might imagine that maybe that's also the case for some of the Brazilian region members, although Paulo nicely already mentioned IBS in his introduction. I don't speak Portuguese, but I could get the main points. So thank you for doing that, Paulo. Anyway, who are we? Well, it's an international biometric society. Our aim is really to promote the development and the application. So it's not only methodology and development, but also the application of statistical and mathematical models and theory and methods in biosciences in general. And of course, that includes agricultural sciences, biomedical sciences, public health, ecology, and many other related disciplines. We're a worldwide society. We have many different regions, and you will see a little bit more about that on the next slide. But just to give you a little bit of an impression, here is RBras, the Brazilian region, which is a big region. And here is where I am located. So that's this tiny little dot there on the map of Europe. So it's nothing compared to Brasilia or to Brazil, but I'm just pointing out that we are not all that far away from each other. And I've been able to visit Brazil several times and also visited Clarice's department, and I always very much enjoyed it. Now, worldwide, we are organized in regions, which are usually countries. And then sometimes a number of countries join and they form a network. So we have 4 networks in total, like the Suzanne network. Many countries in the southern part of Africa have joined one big network. And actually, they currently also have their regional meeting, and I was able to attend their meeting yesterday. Approximately 6,000 members we have worldwide in all these many different countries, and that's about stable over the years. Here you see split up over the different categories of memberships, but so in total we have 37 regions, and then on top of that we have these 4 networks that I mentioned already before. So the good news is we have really members in all continents of the globe, but of course there's still room for a growth. And if you would know of any countries where they do not have an IBS region and where there would be some biostatisticians willing to join our society, just let us know. We have many things that we do, but of course, one of the major things is publishing. We have 2 journals that IBS publishes itself. So the flagship journal is Biometrics, which I hope you all know, which I believe you all know. And then there's also JABES, the Journal of Agricultural, Biological, and Environmental Statistics, which I believe is also quite important and well known in Brazil. We have a newsletter which comes out about every 3 months, which is Biometric Bulletin, and there you can see some news about the different regions, news about the society, what is going on in the society, news about meetings and things like that. And then there's 2 journals that are published by regions of IBS. First of all, there's the Biometrical Journal, published by the German region, and then there's the journal Biostatistics and Epidemiology, which is published by our Chinese region. What we also do is we organize a worldwide conference every 2 years, so it's always in the even years, and I'm really happy to announce to you that our next meeting, IBC 2022, will be held in Riga in Latvia, which is one of the European countries. And of course, it's still a little bit tricky what it will be in terms of traveling and whether traveling will be possible for many of our members. We're still hopeful as vaccination rates keep increasing worldwide. We're keeping a close eye on that. If it would not be possible for all regions to travel, we intend to have also some online version of the conference, or at least parts of the conference could be offered online. But we're still hopeful that we will eventually be able to meet in person in Riga, and I really hope that many of the Brazilian members can make the trip and are interested in joining this meeting. And maybe this is also the right time to invite many of you to submit a contributed paper. The deadline for that is the end of September. Several announcements about this have been sent out already. Check out also, please, the website, which you see the front page here on the screen. You can check it for an overview of the scientific program, which is already known to some extent. So we have the invited program ready, we have the short course program ready, and if more information becomes available, that will always be posted here on this website. About 1 year, a little bit more than 1 year ago, we launched a new website for the General Society, the RBS website. The previous one was pretty old-fashioned and had to be updated, was too static and did not allow interaction between our members. So many new features have been included in the new website. So please also check the website for announcements, for news about regions, about the society, and so on. Also about our meetings, including also regional meetings. And there's also the communities, which allows all our members to interact with each other. So if you have something to share, news that you think is probably also of interest to the majority of our members, please don't hesitate. Post it on the membership community, and then you immediately will get some reactions, hopefully, or you can start some discussion if you have specific questions about a statistical topic and so on. That's all possible within the society website. So I would like to conclude here. Thank you very much for your interest. Thank you very much for joining the RBras meeting. I hope it's going to be a very fruitful and good meeting, and I'm pretty sure, having looked at the program, that will be the case. If there's anything we can do from the society to help the region or to help individual members, please step forward, let us know. Here you see the general email, and then definitely someone of the staff members will respond to you, but feel free to also contact me if you prefer that, with suggestions, or if you say, I want to be more prominently involved in the society and I'm willing to take up some positions or to join some committees, let us know, and we will be happy to discuss that with you. Thank you very much for this part of the meeting. Thank you.
Thank you very much, Geert. And now we are introducing your talk, Geert. It is really a pleasure for us that Geert agreed to give a talk and to be here with us as the International Biometric Society president. A bit more about Geert. Geert is a professor of biostatistics at Catholic University of Leuven and also at Hasselt University in Belgium. He is the director of Biostat and the vice director of the Inter-University Institute for Biostatistics and Statistical Bioinformatics between the Catholic University at Leuven and also University of Hasselt. He published more than 200 peer-reviewed papers and several textbooks on various aspects of longitudinal data analysis. He has received many awards during his professional career. He taught a large number of short courses for academia, industry, the regulatory authorities, and at scientific meetings, including Piracicaba. He visited our department several times. He has served and serves on a variety of committees of the most important statistical societies, including International Biometric Society, American Statistical Association, International Statistical Institute, Royal Statistical Society, and Catholic Society. He currently is the president of the International Biometric Society. And now, Geert, the word is yours for giving your talk. Thank you very much to being with you.
Thank you very much, Clarice, for the very long introduction. Way too long. I don't deserve that, but thank you anyway. So let me again try to share my screen. Share. And there it should be. All right. Here it is. So I've been looking for a topic to present to you today, which I hope will be appealing to many applied statisticians in various contexts, which is the topic about how to correct for baseline covariates in longitudinal clinical trials. Because if you're working as a biometrician, you often have involvement in randomized experiments, and here I call it clinical trials because I'm really working in a medical context, but you can of course have very similar experiments in other contexts. Now, the motivation for the work that I will present to you today is an analysis that we did quite some time ago of observational data, observational longitudinal data, and we got very unexpected results. And that was like the key motivation to start digging into this problem. And it took us several years to work out the mathematical details behind it. And I'm not going to present you all the mathematics. I will just give you the intuition behind it and explain it and show it with some case study. But it took us several years. And while we were doing that, we realized that this also would have implications for the analysis of randomized studies, including clinical trial data. And so a little bit of that journey in the context of a very specific case study is what I will share with you today. And more specifically, I'm going to look at the data published in a journal, a BMJ journal here, which is a very simple setup. So here clinicians wanted to study treatments for chronic headaches in patients in primary care, and they really wanted to know whether it would be helpful to give these patients acupuncture. So that's this treatment where they use needles to help to cure patients. And the objective is just a randomized controlled trial. 401 patients have been randomized. All these patients have chronic headaches, predominantly migraine, and patients were randomly assigned to either the control group or a treatment group, let's say. And the control group also got some treatment, but that was just the standard care from general practitioners, while the, let's say, the active treatment group would, on top of the standard care, also have the opportunity to attend some acupuncture sessions. And hopefully acupuncture would then help these patients better than just the standard care from the general practitioners. The outcome measured was, well, there were several outcomes, but the most important one, which is also the one that we will look at here, is headache severity. And headache severity is measured using a Likert scale, ranging from 0, which is no headache at all, up till 5, which is extreme intense headache. And this is measured 4 times per day during 4 weeks. So each time a measurement is to be taken, they follow up these patients for 4 weeks, or they ask these patients to complete like a logbook. And 4 times a day, these patients have to score their headache severity at that point in time, at that point of in that time of the day. And then they have so many measurements, they sum them up, they average them over the days, and they rescale it to the range 0-100. So 100 means very intensive pain for a longer period of time, because we're talking about 4 weeks periods always. 0 would mean that there's no headache at all. Here you see the patient flow. So the most important thing is that 400 patients, about 400 patients were randomized, 196 were in the control group, 205 patients were in the acupuncture group, and the study had a longitudinal design. So the first measurement was taken at baseline, and basically that meant the 4 weeks just prior to the initiation of the treatment. Then after 3 months, they did this again, and then a last time, a third time after 1 year. So we have 3 observations per subject, 3 observations per patient. But there are, of course, like in many longitudinal studies, there were some patients who drop out prematurely. More specifically, 106 patients did not make it until the end of the study. At first, in this presentation, I will ignore these 106 patients. So I will first look at those patients for which we have all the 3 measurements available. And then later on, I will come back to that, and I will include also the 106 patients who dropped out, just to see what would be the impact of that on our general findings. Here you see the individual profiles. So on the left-hand side, you see the control group. On the right-hand side, you see the acupuncture group. And what you observe here in these plots are lines, all representing different subjects. So every subject is represented by 1 line, and the outcome is the headache severity as a function of the time expressed in months. And what we clearly see is that there is some skewness in the data sets. We have many low profiles and only a very few high profiles. So because of that, we will use a logarithmic transformation of the outcome to get a much more symmetric distribution. If we then look on the log scale of the outcome, if we look at the averages at all the 3 time points for the 2 different groups separately, and we also look at the standard errors of the mean, we get the following picture here. And then you see that there is indication that the patients do improve, so the severity gets lower over time. It's not entirely linear, but we also get an impression that it's more steep in the acupuncture group than in the control group. Now, the fact that this is not a linear evolution, and that it's the evolution is more steep at the beginning and then slows down, that's something that we will handle using a transformation of the time axis. And this is not a necessary condition, but it's just to have a very simple model to illustrate the methodology and the findings that we have here. And we want to do that in a very simple, a very basic model without higher order terms or without any complex models. So I'm going to use a logarithmic transformation of the time, and then we will assume that the outcome for a particular subject I at a particular point t in time, that this can be well represented for each subject by a straight line. A straight line where the time is now logarithmically transformed, of course. And of course, since measurements will never follow a perfect straight line, we will allow for a residual term epsilon I here, indicating that the actual observation of a particular subject at a particular point in time may be slightly different from that straight line. If you then look at that straight line, then you see that it has an intercept, which is quite obvious here. We also have a slope, but both the intercept as the slope are decomposed into a beta parts, beta 1 here or beta 2 for the slope in the first group, and then likewise beta 3 and beta 4 in the acupuncture group. And then on top of that, we have a parameter B1I or a B2I. Now, the beta parameters tell us what is the average intercept in the control group, what is the average slope in the control group, and then likewise, what is the average intercept and the average slope in the acupuncture group. So if we only look at the beta part of this model, this would then tell us what is the average evolution in the control group in the population. What is the average evolution also in the acupuncture group in our population? And the other parameters, so the B parameters, are subject-specific parameters expressing how the evolution, so how the straight line for the ith subject differs from the average evolution. So B1I would tell us whether the intercept of subject I is higher or lower than the average intercept in the group to which that patient belongs. And the same for the B2I. If B2I would be positive, then we have a patient where the slope is higher than average. If B2I is negative, then we have a patient where the slope is lower than average in the group to which that patient belongs. So that's just to understand what all these parameters mean, how to interpret all these parameters. And these regression parameters, beta 1 up till beta 4, as I mentioned before, they model the average evolution. And that's because we will always assume these subject-specific parameters to have mean 0, so that on average, the evolution is represented by the beta parts of the model. The model that you've seen there is nothing else but a very special case of this general model. And what you see here is as notation yi, which is the vector of all the measurements for the ith subject. So you just combine the 3 observations for a single subject in a 3-dimensional vector, and then you can write down a linear regression model. But now we do not have the traditional linear regression model, because we now have 2 sets of covariates and we have 2 sets of regression parameters. On the one hand, you have the part with the beta parameters, which models the average evolution. On the other hand, you have the part with the subject-specific parameters, which models how the evolution of that particular subject differs from the average evolution. And then, as always, we have the traditional error terms epsilon I here, which is a vector of residuals, only telling us that the actual observations slightly deviate from that straight line for that particular subject. Now, since these parameters BI are subject specific, and if we assume these subjects to be sampled from a population of subjects, we can then also say, okay, these BI parameters have also been sampled from a population of parameters. So we will typically assume these BI parameters to follow some distribution. And as I indicated before, we will always assume that these subject-specific parameters have mean 0, and most often, because of mathematical convenience, people assume a normal distribution for these subject-specific parameters, and then we end up with a normal distribution with mean 0 and some covariance matrix D, and then adding on top of that a normal distribution for all the residuals, we end up with the following general model. Now, if you use all these distributional assumptions, then you can quite easily derive that the marginal distribution for your outcome vector is just a normal one with a mean xi beta, and we're not surprised by that because we already mentioned several times that the beta parameters model the average evolution in the population, and then the covariance matrix has a very peculiar, very strange parametric form where you see that one component comes from these subject-specific random terms in the model, so the random effects in the model, and the other part here comes from the residuals. So what you have is nothing else but a multivariate normal distribution, but the covariance structure has a very particular parametric form. That's what this general linear mixed model is assuming. And once you have that marginal distribution, you can write down the likelihood, you can estimate all the parameters in that likelihood, and that basically gives you your inferences and your results. And here are the results for the acupuncture data set. And what you see here is the two intercepts in the two groups, also the two slopes in the two groups, the estimate standard errors p-values, and then we also looked at the difference between the two intercepts, which is not significant. And of course, that's not really a surprise because we have a randomized experiment here. What is much more important is to see that the two treatment groups indeed have a negative slope, which is highly significant, and that the difference between these slopes is also highly significant. So the acupuncture patients really show significantly more improvement over time than what you observe for the control patients. Now, from now on, I will only focus on these slopes because these are the parameters of interest. If you set up a longitudinal experiment, it is because you're interested in studying how people evolve over time. So we want to know what is the evolution over time of these subjects, and that means that the parameters that are really of interest to us are these slopes beta 2 and beta 4, and then probably also the difference between these two slopes. So from now on, we're only going to focus on those parameters. Now, what I did not tell you yet is that the randomization was done using minimization. So what you then do is you don't just flip a coin to decide in which group a patient will belong, but you take into account some other patient characteristics such that you can use a biased coin, let's say, where there's a little bit more weight for one group than for the other group, depending on the distribution of the covariates at that point in the randomization procedure. So it's a little bit similar to stratified randomization, which also aims at having two groups or multiple groups, if you have more than two groups, that have the same distribution for a number of key characteristics of the patients. And the minimization variables that were used here were the age of the patient, the gender of the patient, whether the patient had migraine, so whether the headache was of the type migraine, also the chronicity of the disease, so that's the number of years a patient already is suffering from these headaches, and then the frequency, that's the number of days in that 4-week baseline recording period during which headache was experienced. So some days a patient has no headache at all, and other days the patient has headaches. Well, we just count here the number of days with headaches in that 4-week baseline recording period. Now, guidelines then say that all your analysis, whether you use minimization techniques or whether you use stratified randomization, the guidelines say that you need to use all these covariates and correct your analysis for those covariates. So if you look at FDA guidelines or EMA guidelines in Europe, they all say the same thing. If you have such covariates used in the randomization procedure, you have to take them into account in your analysis. And that can, of course, quite easily be done. The only thing you need to do is take the model that we had, extend the model with additional terms for all these covariates, and you then again have a model. It's a more extensive model, but it's still a model that fits in that general formulation of the linear mixed model. So you can still happily continue using your favorite linear mixed model package, and all your inferences will follow from the general linear mixed model methodology. Now, the research question that we are now want to look into is whether, if we do this, so if we correct our analysis for these baseline covariates, whether we will suddenly get different estimates for the parameters of interest, which again, these are the slopes, whether we would get different p-values, whether we would get different confidence intervals, inferences in general, yes or no. What's going to happen? What is the impact of doing this? What if important baseline covariates would have been omitted? If you forgot about some of those, would you then get wrong results? What if that baseline model is misspecified? Because if H was one of these covariates and you just correct for H, then as you all know, you're implicitly assuming that there's a linear relationship between H and your outcome. Well, what if the relationship between H and the outcome is not linear? What if you would need a quadratic term, or what if you would need some transformation of your data? And you misspecify that model, how would that affect your conclusions about these slopes? And then finally, if one wants to correct for differences between patients at the beginning of a study, just including covariates in a model is only one possible solution. Another solution that people often use is what I call here longitudinal analysis of covariance. And let me first explain what that is, because we will also take a look at that technique, because we want to see whether we get different results if we just include additional covariates than if we just use longitudinal analysis of covariance. Now, what is longitudinal analysis of covariance? The idea is very simple. The idea is, okay, if we want to correct for differences between the subjects at the beginning of the study, let's just use the baseline value that has been measured for our outcome, and let's use that baseline value as an additional covariate in our model. So you just take yi measured at time t equal to 0, so the first observation for that subject, and you include that, you add it to your model. Now, of course, the moment you do that, you can no longer use that measurement as part of the outcome vector. And that's the reason why you see here that we start modeling the data from t strictly larger than 0 onwards. So what you basically do is you remove that baseline value from the left-hand side of the equation and you move it to the right-hand side of the equation. So instead of treating this variable as part of the response vector, you include it as a covariate. Now, this model is, again, of a special case of the general linear mixed model. So again, you can easily fit this model using classical linear mixed model methodology. Now, let's take a look at the results if we now apply this. And what you see here first is the original linear mixed model. And again, I'm only focusing on the slopes now. The original linear mixed model, and you've seen these results before. And then I extended the model with the additional baseline covariates, such as age, gender, migraine, and so on. And here you see the results after correction. And you might carefully compare these two tables, and then you will soon realize that the estimates are just the same. They're exactly the same. And not only the estimates are the same, but also the standard errors are the same, which is quite strange because the additional covariates that we have added to our model were extremely significant. So the p-value is less than 1 out of 10,000. So intuitively, you would expect that if you include additional covariates that explain a lot of variability in your data, and that's obviously the case here, you would then expect to see at least that because you have explained more variability, that the standard errors get smaller. So even if you would still get the same estimates, you would expect to see smaller standard errors, but apparently that's not the case. So your inferences, p-values, confidence intervals, and everything that is related to that would remain completely the same, whether or not you correct for these baseline covariates. And that's something that, of course, that raises some questions. Why is that? Is that generally applicable? Will that always hold, or is there something peculiar in this data set? And is that only specific for this data set? So this is something that we have to look into. What about longitudinal analysis of covariance? Well, here again, you see the original mixed model, and you've seen that now already for the third time. And then I removed the baseline outcome from the become part of the model, and I took it into the model as a covariate, as I explained before, and then you get those results. And then you see suddenly that you get different results. So using the baseline value as a covariate immediately not only gives us different estimates for the slopes and for the difference of the two slopes, but it also gives us quite different standard errors. So apparently what we observed before on the previous slides does not hold if you have longitudinal analysis of covariance. And the question now is, why is this the case? What is going on here? And now, what is the best procedure in practice? Well, it took us actually a few years to be able to mathematically prove what is going on. And we eventually were able to prove the following general results. And I'm not going to talk about the mathematical details, but the result states that estimates as well as standard errors of slopes, so of longitudinal effects, do not depend of cross-sectional terms in your model. So they do not depend on the cross-sectional effects, the cross-sectional covariates that model differences between your subjects at baseline in well-formulated models for balanced data. Now, what are well-formulated models? Well, well-formulated models, or well, there's literature about that, and you see a reference here, but in summary, it means that you don't use models with higher order terms if you also don't have the lower order terms. Or, for example, you would not put in a random effect for time if you also do not have a fixed effect for time, and so on. So it's like a restriction of the models, but it's really a minor restriction. In most situations, people always use well-formulated models. And I will come back to that later on. But so the bottom line here is that whether or not you put in additional covariates, you get exactly the same results. Now, why does that explain what we have observed in our case study analysis? Well, first of all, if you put in these additional covariates, the general results states that you will get the same inferences, you will get the same estimates, same standard errors, p-values, and so on. So, and that's exactly what we obtained. So that's exactly what we observed in our analysis. So including these baseline variables such as age, gender, migraine, and so on, it has no impact at all as long as you're only interested in these inferences for the slopes, for the longitudinal effects. But once again, if you set up a longitudinal study, that's typically the case. What it also means is that misspecification of your baseline model is not important. So again, if you would put in age with a linear factor, but in reality, you would need a quadratic term, and you omitted that, that has no impact, because whether or not you add that quadratic term to the model, it has no implications at all for your inferences, for your longitudinal effects. So that's pretty good news, because it means we don't have to worry all that much about these baseline covariates. You can include them if you would want to draw inferences about them, but if not, then just forget about them, and you're not going to lose anything, and you definitely will not lose any efficiency. What about the longitudinal analysis of covariance? Because remember, the moment we used the baseline value as a covariate, suddenly we got different estimates, we got much higher standard errors. Well, why is that? Well, if you take that longitudinal analysis of covariance model and you would remove, so you keep the same model, but you only remove that baseline covariate, then nothing is going to change, because of the general result that we just discussed. So putting in that baseline value as a covariate or not has no implication. But if you remove it, then you also have moved it away from the response vector. So basically what you're doing is you're just throwing away the first observation for all your subjects. And that means that you have to lose efficiency, because 1/3 of the observations in our data set, of the acupuncture data set, is then thrown away and is not used in any of the inferences that we conduct. So the bottom line here is that this is not a good idea, because the only impact is that you're just inefficient in your inferences. So it's much better to include your baseline value, but then you have to include it as a response and not as a covariate in your model. And if you do it, you can then still gain efficiency. You're then back in the traditional linear mixed model, and then you don't have the risk of losing too much efficiency. Now, what about this alternative technique that we have not discussed yet, but which is still often used in, especially in clinical trials, and which people call the MMRM model? And MMRM stands for Mixed Model for Repeated Measures. And I believe this is a very poor terminology, because it has nothing to do with a mixed model. What is the idea behind the MMRM? Remember, our mixed model implied this marginal model, and we discussed that this is a multivariate normal distribution with a particular mean, and then a very peculiar, a very specific parametric covariance structure. Well, the MMRM says, well, okay, we have a very parametric form here for the association structure. Why not just replace this by a general covariance matrix sigma? So don't make the assumption of having a very parametric shape here, a very parametric format. Let's just replace this covariance matrix by a general covariance matrix. And in the acupuncture data set, sigma would be just a 3x3 covariance matrix. And then, of course, you end up with classical multivariate linear regression or classical multivariate analysis of variance. And because this is not necessarily implied anymore by any random effects, I believe that this terminology, call this a mixed model, is actually not a very good choice, but that's just the way it has been done historically in the literature. Now, when you use such a multivariate linear regression model, then you still have many options for your mean structure. You can continue to use a parametric model for the mean, a little bit similar to what we did in our case study, and you can use, for example, straight lines on average to describe your population. But you could also say, okay, let's put in time as a categorical variable and not use any assumptions about the parametric evolution of our outcome as a function of time. And if you do it categorically, you then just fit an average for each combination of your treatment group with the time at which measurements have been taken. Well, here you see the results of the MMRM analysis, and as effect that I look at, I looked here at the change from baseline. So you use this MMRM model. I included time as a categorical variable, but then I still estimated based on that model the change from baseline. So you look at the fitted value at the end of the study minus the fitted value at the beginning of the study, and that's estimated in the control group, in the acupuncture group, and of course you can also look at the difference between these two treatments. And if you repeat that model with the additional covariates that were used in the randomization procedure, you again find exactly the same results. So apparently what we observed for the linear mixed model also holds for the MMRM model. And the explanation, of course, is that this covariance structure, sigma, you can still obtain it from a linear mixed model as long as you put in sufficient random effects. So, for example, in the acupuncture data set, sigma was a 3x3 covariance matrix. Well, if you would use or formulate a linear mixed model with 3 random effects, then that model would imply a marginal model that is mathematically identical to the MMRM model. So whatever properties hold for the linear mixed model would also have to hold for the MMRM case. So whether you use a purely mixed model or an MMRM analysis, the theoretical result still applies, and you still do not have to worry about baseline covariance. What about endpoint analysis? What is an endpoint analysis? Well, in a randomized experiment, because patients or subjects or animals or plants were randomly assigned to the different treatment groups, we know that on average, the different groups are equal at baseline, okay? At least in a sufficiently large sample, but definitely in the population. So the idea is then sometimes that we don't have to really look at slopes, but that you can just look at the endpoint. So at the final observation or the final outcome value at the end of your study, because a difference in evolution should then automatically result in a difference at the end of your study. And you can do that based on a linear mixed model, or you can do that based on an MMRM model. All you do is you fit your model, and once you have your model fitted, you then look at the predicted value at the end of the experiment, and you compare your different treatment groups for that predicted value. So you can use that very easily based on a linear mixed model or an MMRM. And I've done that here. So here for the original linear mixed model, on the right-hand side for the MMRM model, where I use time as a categorical variable, and under both these models, I have predicted the final observation, so that the outcome at the last measurement, so after 1 year, for the two treatment groups, and then also the difference, and then I repeat these two analyses, correcting for the additional covariates. And then you see that you do no longer get the same results. If we focus, for example, on the original linear mixed model, then you see that the slope for the control group goes from 2.8 to about 1.4. So that's almost like half of the original effect that we obtained. And also the standard errors differ, and therefore you get completely different inferences. And the question is then, why is that? Suddenly you still use the same model, you just look at a different estimate, basically, and suddenly the so-called robustness property, the fact that you don't have to worry about which covariates you take into the model, that no longer holds. Well, the reason is, of course, the following. What is an endpoint? The endpoint is a combination of the starting point and the evolution. The starting point, that's measuring cross-sectional differences between your patients. These are differences at baseline, at the beginning of your experiment, while the evolution tells you something about longitudinal effects. Now, we've already extensively discussed that these longitudinal effects, the slopes, we called them, that these slopes are quite robust, and they don't suffer from additional covariates, yes or no, in the model. But of course, the cross-sectional part of the model, that will be affected by additional covariates. So if you put in or you do not put in additional covariates, your cross-sectional estimates will be affected. And because of that, also your inferences for your endpoint will be affected. So the bottom line here is that it's not a good idea to look at an endpoint analysis. It's much better to study trends rather than studying endpoints, because trends are like almost orthogonal to what is happening in these baseline differences. Now, going back to the theoretical results, there were two conditions. First of all, we had to assume that we had well-formulated models. And I said, well, usually in statistics, we always use well-formulated models. That's not always the case, and often, or sometimes in clinical trials where people randomly assign patients to subgroups, people sometimes are inclined not to use well-formulated models, because we know that due to the randomization, the two treatment groups cannot differ at the baseline. So that sometimes leads someone to not include a main treatment effect, and then impose the fact that your two groups should be equal at baseline, and then only look at the slopes afterwards. Well, if you do that, and you remove the main treatment effect from your model, and you do repeat the analysis without or with the additional covariates, then you see that you get slightly different results. So our robustness property no longer holds. It's not that you see major differences, but you do see some differences. So it's a good strategy in general to always keep that main effect in the model, even if you are in a randomized study, because then you know that you buy some robustness of your model and of your conclusions with respect to baseline covariates that you might or might not include in your model. And then finally, the second condition was that we needed balanced data. And that's, of course, the reason why I focused so far only on the subjects that have had all three observations available. But what about unbalanced data? Well, we can easily check that. And if you include now also the 106 incomplete profiles in the analysis, and you take the original linear mixed model and you compare it with the model that is extended with additional covariates, then you will see that you no longer get exactly the same results. The changes are really very minor, and you can actually prove mathematically that there's very good reasons to believe that in general, if you omit important covariates and you have unbalanced data, that you might get small biases in your results, but that these biases really will be very small and that there's no reason to really worry about this. So it turns out that the general property that we have discussed and before does not exactly hold if you have unbalanced data, but it's almost holding if you have unbalanced data, and there's nothing really to worry about. So if I try to summarize what we have now seen and what we have observed in this case study analysis, together with the theoretical property and then the implications of that property for the analysis of longitudinal clinical studies, or longitudinal randomized studies, I should say, it is that the correction for baseline covariates has a very limited impact on inferences for slopes. So once again, we're only talking about inferences for slopes here. If you're interested also in getting inferences for, let's say, baseline covariates in your model, then those inferences can highly be affected by the presence of some other covariates. But as long as you're only interested in slopes, then it doesn't make a difference whether or not you correct for additional baseline covariates. The results hold for the linear mixed model as well as for the Mmrm model. They hold for balanced data as well as for unbalanced data. What is important is that we always have to keep in the main treatment effect, even if we have a randomized study. And another important aspect is that if you need to choose an estimate, it's much better not to focus too much on the endpoint only, but study slopes, because slopes are very robust with respect to what you do in the baseline model. What is not a good idea is to use your baseline response measure as a covariate in your model, and just do analysis of covariance, because the only effect of that is that you lose efficiency, and you can really lose a lot of efficiency, as we have seen in our case study. Now, there's one additional note that I should add, and that is everything that we have discussed here holds for linear models only. So don't just immediately apply that also to generalized linear mixed models or to nonlinear mixed models, because while I have not really studied that in detail, I'm quite confident that we can say that the results will no longer be holding in these other families of models, because the mathematics that have led to this general result that I have presented here are really very specific to the linear model. So once again, keep in mind that whatever we have concluded here only holds for linear models. And on that note, I really would like to end my presentation, and I thank you for your attention, and I'm definitely happy to answer any questions if there might be any questions. Thank you.
Thank you very much, Geert, for this wonderful presentation. It is always very good to hear you talking. And I would like to see if some people from YouTube have some questions. But first, I would ask the people who are in this link if they have some questions for Geert. And then Tassiana is taking care of the question from YouTube and will send to me. Erwig, do you have any question?
Thank you very much, Geert, for this very nice, interesting, and also clear presentation. And I do have a very similar impression when I was working with data that are from this class you were describing right now. Data that says something over time, measured several times over time. Then I also sometimes did it in a way to use the base measurement as an offset. Mm-hmm. And sometimes I did it as you just previously formulated, that it's the better choice to use the baseline measurement as another response variable. So what I sometimes do is not to provide the baseline measurement with an extra parameter like you did it with beta 5, I remember, mm-hmm. but simply said that's an offset. And what the model is doing with the offset is to describe the change, what's going on, starting with the value of the offset. Is this a similar experience you had?
I've never tried it, to be honest. I would think, well, my impression, what I think, if I just think of the mathematics behind this general property, I think you would still have the same conclusion. Mm-hmm. Well, of course, your inferences might be slightly different when you add an additional parameter or not, but you would still have that if you remove that parameter or you keep it in, that this will not really change your results very much, because the thing is that in the mathematics behind it, it's not the size of that parameter that matters. What is mattering is the fact that you can rewrite the model in such a way that your cross-sectional terms become like orthogonal to the longitudinal terms. And that it's more a property of the covariates rather than a property of the parameter values associated to these covariates. And because of that, I'm inclined to say that I would expect to see similar effects happening, like what we had with the additional parameter, but I would have to check it to be really absolutely sure, because I've never tried it.
Mm-hmm. And another question, you mentioned the mathematical details, so I'm pretty sure you do have a paper on that. Can you shortly tell us where the publication can be found?
Yeah, there is this main conclusion. Well, the main result is published in Biostatistics, and that's not even a recent paper, because as I mentioned in the introduction, this whole research started when we were looking at observational data. And then if you have observational data, you always end up with questions from clinicians who say, shouldn't we correct for this and this and this and that? And before you know, you have like 10 or 20 covariates to correct for. And it was just by coincidence that I happened to notice that whether I corrected for all those covariates or not, I got exactly the same results. And I couldn't understand it. So, this whole area of research started with observational data, but it's only when it was finished that we started to realize that this, of course, also has implications for clinical trials. And that's the reason why I then put together this presentation now in the context of clinical trials, because especially in these clinical trials, you often see these Mmrm models. With observational data, you don't have that, because with observational data, measurements are often taken at all different time points. But with MMRM, you have nicely balanced data sets, and that's when people start to use this MMRM. Because that's applicable in clinical trials. So I was very keen on seeing whether it would also happen there. And of course, it must happen because you can immediately see it as a special case of a linear mixed model, and that was confirmed.
Thank you very much for your clarification.
Thank you.
Thank you, Herwig. One question from YouTube. I was wondering which of the methods used do you believe is more efficient? Raissa, Luna is asking you.
Well, I would, based on everything that we have seen in both observational data and clinical trials, I would, well, my preference would be to just use a linear mixed model, because it's so robust. And it's, I mean, here we have looked at robustness with respect to additional covariates that you put in your model. But we also know from others who have looked at this, but also part of our group has looked at this, that it's also very robust with respect to distributional assumptions that you make. So you can only like gain if you use that model, knowing that you don't have to worry too much about distributional assumptions, about additional covariates in the model or not in the model, or if you put them in the model, you don't have to worry too much about whether you put them in the right parametric form in the model. So these are all major advantages that you have, which you sometimes lose if you use alternative methods. And that's why I'm well, quite confident that in many situations, this is like a very good choice for your analysis. And it is efficient. I mean, if you compare it to what we've seen for the longitudinal analysis of covariance, there you only lose efficiency. So why would you do that if you don't gain anything?
I think we have just time just for one more question before Herwig talk. There is one question from YouTube again, and that this goes which I would ask him. What if the normality condition doesn't hold? This is the case of, now I am completing it. This is the case where your response is from a scale, and the Likert scale. Mm-hmm. And he also asked, would you have a non-parametric method to analyze that data, or would you have other type of model you could use for this data?
There's not much available if you really want to do it completely non-parametric. What is done is there is quite some literature on how robust all these methods are with respect to distributional assumptions. So, of course, if you really have very discrete data, I would never use a linear mixed model. Then I would move to either GEE or generalized linear mixed models, and then it's a completely different story, of course. But as long as you have like ordinal data or data that are let's say almost continuous, or that where you say that it makes sense to interpret the quantitative, the outcome on a quantitative scale, I would not worry too much about the distributional assumptions, even knowing that probably the normality assumption is not satisfied. Because the other thing is, in these linear mixed models, checking the normality assumption is not straightforward. What people do all the time is they look at the so-called empirical Bayes estimates, which are the predictions for these random effects, and then they use a QQ plot or a normality test for these random effects, and you can mathematically show that this is flawed. It doesn't work. Because you can have, I mean, this has to do with Bayesian methodology. These are posterior means, and often based on very little observations, because very often you have subjects with only, let's say, a handful of observations. And then what you often see is that your prior distribution, which is the normality assumption, is dominating your results, because you just don't have data to contradict that prior assumption. So if you're not careful, you get to see a nice normal distribution, while in reality, it's not normal at all. So that makes it so difficult to check the assumption. And that's why I'm so happy that in these linear mixed models, one has been able to show that the normality assumption is not very crucial. Because if it would be crucial, it would become very difficult in practice to use these models, because you would have an assumption which really is very crucial for your results, but which is very difficult to check. So now okay, it's not so easy to check that normality assumption, but I don't care too much about it, because I know that my inferences will be very robust, unless if you have very, very small data sets. But non-parametric techniques, no, there's not much available for that, unfortunately.
Okay, thank you very much for this very interesting talk.
Thank you. You're welcome.
I hope to have you here in Piracicaba.
I hope so too.
In a short future.
Yes. Okay. Thank you
very much, Geert, for your presentation and for being here with us.
Thank you.
I pass the word now to Paulo.
Hi again to everyone. Now it's my great pleasure to introduce you Erwin Friedl. Erwin holds a doctoral degree in science and a venia docendi in statistics, both from Graz University of Technology. Erwin is a visiting professor at University Paul Sabatier in Toulouse, France, and also at University of Florida at Gainesville in the United States, and University of Ljubljana in Slovenia, and the Higher School of Economy in Moscow, Russia. So he holds visiting professorships in 4 universities. Between 2004 and 2014, he was the editor of the Austrian Journal of Statistics, and between 2005 and 2014, he was editor of Statistical Modeling and International Journal. Erwin currently works at the Institute of Statistics at Graz University of Technology in Austria. He is particularly interested in applying mixture models in practice. Thus, he utilizes them in case of nonlinear regression models, histogram estimation, or even estimating a specific population size. Erwin, I would like to, on behalf of RBras, I would like to thank you very much for your availability. It is indeed a pity that we could not make it in person, but that's the best that we can get. So the floor is yours.
So thank you very much, Paulo, for inviting me to give my impression of working with mixture models, and I prepared some slides that are about what to do now. How to find my slides now?
We always have technical issues.
No.
We can see your screen now.
But not my slides. I'm trying it again.
Okay.
So is it the whole monitor or only a window I should?
Usually I share the whole screen so that I can move around, but you can select only the slides.
Oh my goodness. No.
Oh, that's okay. We have that every day, so that's now we can see your screen.
But not my slides.
No, we are looking at the browser, I think.
Oh my goodness.
Maybe if you share the whole screen.
Oh my goodness. I'm doing something definitely wrong.
No, you are sharing, I think, the browser, and then we see.
So I'm closing the presentation. Good. That was an important thing. Now again,
So if maybe it's easier for you if you share the whole screen, and then
okay.
you just select you put the slides in your screen, and we can see it as well.
So I'm coming. That's terrible. No.
If you go to your slides, because yes. when you start to share, if you share the whole screen, it will be the browser in the top. If you go to
so on the screen there is my presentation open at the moment, and now going back to my web browser, I like to share it.
Yes. So if you go present now.
Paulo, quer que eu compartilhe?
Maybe Eric, if you prefer, yeah. Tatiana could share because she has your slides.
If that helps.
Yeah, but then you will have to say when you need to change them. I don't know if that's handy for you.
Mm-hmm.
But if you go and share your full screen and then you put your slides in your...
I think I got it.
Okay, great. Oh yes, now we can see. Now it looks better. Now it looks like a PDF. Perfect. So the floor is yours.
So the next problem simply is how to go further on the next page.
I think you can do Control L and you get full screen, or you can just go like that. I think it is fine. Or if you prefer the full screen, you can do, I think, Control L. It should make the full screen for you.
Okay. So is this the first page you see?
Yes, we see mixture models in practice.
You see now the second one?
Yes, we see 3 plots.
Okay, wonderful. So I got it.
Okay, please, Eric.
Apologize.
No, nothing to apologize. So floor is yours.
That's stupid, but anyway. So it's really a big moment for me to give a presentation right now, sitting in Graz, Austria, and right after Geert Verbeke. So for me, it's really a challenge, and I hope that I can stand the expectation, so to say. Geert said a lot about mixture models in practice. I will show you some typical applications of. He was talking about mixed models. Sorry about that, and I will talk about mixture models. So it's really something different. Sometimes both these model family are strongly related. I will not talk about the relationship. I will simply straightforward give you my impression of what goes on or what could be done in the analysis using mixture models in practice. So this is joint work with Peter Scheibelhofer, Sanela Omorovic, and Bettina Grün. Maybe you know Bettina. She's really a very famous Austrian statistician working in Vienna at the moment. So here is the package Bettina Grün has developed, and the package is an R package, and the R package is called FlexMix. So here are 3 typical applications, and the first application here is simply check out a histogram, and this is the very well-known histogram of eruption times depending on weighting and the other way around. So here is a model model-based clustering. That's Fisher's iris data, and here is a typical example she is providing when motivating flex mix. That's a mixture of generalized linear models. So what we are usually interested in is to find out which part of the data belongs to which component, and that's the idea behind what we understand under mixture models. So it would be great to identify this red component and separate it from the blue one, or here in model-based clustering to identify the 4 different groups, subgroups, or even here to see what's going on if you mix up generalized linear models. So what we, in the next step, really like to see is the structure behind. So the blue dots, they are a linear regression model. The red one are more following a quadratic model. So you see here, there's open space for an extension, and the open space for extension is about my second example I present you. That's mixing generalized nonlinear models. So this is a really highly parameterized model situation. Actually, again, we want to identify which observations belong to which group. So this is our first task, and the second one is even estimate the models that exactly are determined by these 2 pieces, 2 groups of observations. So here is, for example, the model fit. So what comes next is I will introduce you a practical example I was involved in by which falls into this first category, and then later on my second example falls into this 4th category. So I will analyze histograms using mixture models, and I will analyze nonlinear regression models using mixture models. So here we go. That's application number 1. It's about a CSAM image of wafer. So a wafer is, you should understand it as a binding situation of 2 different pieces, and on each of these pieces there are chips on. So that's a situation I was involved in the AMS. AMS is an enterprise producing chips, producing wafers. It's for Astra and Microsoft Information. So we are producing wafers, and the problems are bond voids between the 2 layers. So 2 layers, they are bounded together, and the problem is that there is possibly some air included within the 2 different layers. What we do have is we do have images of this wafers, and the total number of such images is 113. And what we were interested in doing is to account for 2 different qualities. Namely, the first one is to check out the quality of the image. I will show you the image in a minute, and to check out the quality of the wafer. So these are 2 totally different situations. It's about the image quality. The image quality is about having a strong or weaker contrast. So by producing one image after the next one, the contrast can change, and we want to control for this change early enough such that the quality of the image is high enough. The second one is about the wafer quality. So the AMS AG is not interested in producing wafers and selling their wafers of low quality because that's very costly. So wafer quality is one aspect, image quality is the second one, and it's good to know that the wafer quality is a certain aspect of the image, or we can use the image in order to discuss the quality of the wafer. So what's the image about? What you see here in blue, or here with an air gap included in white, or here as a third instance green and blue, is exactly a cut through the wafer. So the wafer is cutted, and you see, using this acoustic microscopy technique, there is a high transmission of the acoustic waves if it's one and the same material here in the wafer. If there is some air included, there is a reflection going on, and the reflection produces a different dot exactly where this happened on the image. Or if there are 2 different materials being bounded, then also there is a partial reflection going on. So this machinery, this technique allows to build images. And I give you here examples of two different images. The first one here on the left is an image where the contrast is pretty nice. It's very strong. And you see this bond voids, these air inclusions, very easy. You can recognize it directly from this image. Here on the right side, it's a different sort of an image. It's another wafer, but the contrast of the image is really poor. It's very weak. And it's not that easy to see that this is something light compared to that one, which is something dark. So what we do is we are reading in the data, these image data, and I was first, when I was involved in that, I was really surprised that the number of pixels here is 22.7 million. So it's an extremely large data situation, but each of these 22 million pixels only provides us with information on the grayscale observed at this pixel. And the grayscale is an integer number, a non-negative integer number between 0 and 255. What's important to know is that 0 means absolutely black. So for example, here outside of the waver, and 225 means brilliant white, so far more white than these dots here are. So the first thing I don't like to talk about is a data pre-processing step. So we want to get rid of these outside areas. We also want to get rid of the center point, and even we want to get rid of this circular ring here around, because that's not providing any information about the waver itself. So again, think about how to use, or how can we account for that such an image belongs to a group of images where we are happy with the contrast because the contrast is strong, and how to account that such an image belongs to the other group, image B, for example, here I called it, where the contrast is weak. How can we do that? So first, I read in the data, and what we could do immediately is to draw a frequency plot, like a histogram, I was calling it, where you see the lowest grayscale value here on the left, where we do have a strong contrast, is about 20, and there is one group of grayscales, that the most prominently observed group here between 20 and 70, something like that. Then there seems to be nothing at all up to 106, and there is a second minor little heap. And this second minor little heap is about the light areas on the wafer, the light areas in the image. And this accounts for all the number of pixels where we do have bond void. So this is the erroneous zone of the image, and this is the good zone in the image. The second looks very similar. The only difference is that this light component is much closer to the dark component as over there. So we can immediately measure what I meant by using the word contrast as something like how far apart is the right little heap from the first big heap here. So the distance between the two centers, something like that, the distance between these 2 points. If you think about using a mixture model, then you would say this is maybe 1 or 2 is a mixture of 1 or 2. We will use later on 2 components, and that's a third one. So the distance between the first mean and the last mean, that describes us the contrast. How larger the distance is, how stronger the contrast. So that's the idea, what we like to work with. So what has been done so far? People there and were manually screening the images, and they somehow graded the quality of the image using words like bad, medium, or good, and that's of course very time consuming and not very efficient. So they didn't check out the histograms, they only checked the image photograph itself. So what I like to do is I like to use a statistical model and use a model in order to model the histogram. And I think it's very clear that this can be done by a mixture distribution. If I say finite, I mean something like a 2, 3, or 4 component mixture distribution. So what are the assumptions about the components itself? Because of convenience reason, let me put it that way, we are using normals or gammas. We don't have so far implemented Poissons or other discrete components, because I think here did it in a similar way. We are very close to a continuous situation if we do have grayscales defined on the grid 0 up to 255. So that's the reason to use normal and gamma only. And what we like to do is to find estimators of all the parameters being involved in our model. And we do that, I think that's also very reasonable, by applying the expectation maximization algorithm, DEM algorithm. So here is one of very few technical slides. It's about what is the model about. The model is about here. We have observed mi times a grayscale yi, and yi is the index of the grayscale. So is this index I ranging from 0 up to 255. So this I here essentially is nothing else but the observation itself. I distinguish between running index and the response variable, because as a statistician we are all the time used to say, oh, that's a yi, so that's the ith copy of our response. But this is also in the same time an index between 0 and 255. So using a product means that we assume that all these pixel informations behave independently. And here within the parentheses is our mixture models that uses pi k as the fraction that is the kth component is about. And here is this conditional model, for example, the normal distribution density in the kth component. So each of the components is allowed to have its own parameter situation. So in the normal situation, we do have the kth mean and the kth variance for the kth component. Or in the gamma setting, we do have, if there is a gamma parameterization in alpha and beta, we do have an alpha k and a beta k for the kth component. So of course, the sum of all these fractions have to be equal to 1. And what we like to do is to find out the maximum likelihood estimator. So we have to maximize this marginal density. But this can be much easier done by applying the EM algorithm. So the EM, by its structure, applies to something called the complete sample information. So the complete sample information in our setting would be the grayscale, and because it's about a mixture distribution, this component indicator. So any grayscale belongs to any of the components, and I call this a Z. So Z indicates if I belongs to the kth component. So it's once a 1 and all the other ones, it's zeros. And we again assume that there is independence going on. So we do have a product here over the 256 instances, and we do have another product writing here such one component with its fraction to the power ZIK. So this comes into the density, into the likelihood if ZIK is equal to 1, or comes not into the likelihood if ZIK is equal to 0. So that's very straightforward, very, very standard. So what we are doing now is to calculate the conditional mean of this joint complete likelihood and then maximize that with respect to all the parameters. So here you see that's the t expectation step. So using the proper notation, that's the function q, where theta t and pi t, these are the values of the parameter in the tth iteration, are kept or considered to be fixed, and the function q is maximized with respect to theta here and pi there. And the fixed parameters from the previous iteration, they are part of this posterior probabilities here. So there's a double sum over all the observations. There's the second sum over all the components. MI, you remember, is the number of times a specific grayscale I appears in our data, in our histogram, and here's the log of the likelihood. So what we are doing is we are maximizing the teeth M step, this function here, in theta and in pi. So here we go. If we assume that the histogram can be sufficiently described by a mixture of normals, then our theta parameter in the kth component consists of the two parameters, the mean and the variance. And we can explicitly find the estimator, the maximizer, so to say, for the mixture proportions. So pi k in the t plus first iteration is the mean over all the weighted posterior probabilities. This capital N is the 22.7 million thing I showed you previously. And it's also very clear that parameter updates can be also get in explicit form. So mu k is this weighted mean of the yi's, and the variance is this weighted empirical variance, so to say. It's very straightforward. So the message is that we do not need further iteration in order to find the maximizers. The maximizers can be found explicitly, so we only have to calculate these two parameter updates together with these proportion updates. So if you change from normals, oh, that's another issue, because I told you we are interested in the distance between the very first and the very last component. That was an idea I had to do a reparameterization when the mean is considered. And the reparameterization is that such that the means here are strictly ordered. So this can be done by saying, by reparameterizing mu1 as e to the power alpha 1, then mu2 by adding something positive, and so forth. The big point here is that all the components here, they do not only have their own associated mean, but you see the mean of the first component is also part in the mean of the second, and so in the mean of the last component. So the maximization step becomes much more complicated. And it's not only the complication you have in the maximization step, it's also the numerical instability that comes into. So it's really a drawback. The benefit we will have by easily recognizing and identifying the first mean, the second mean, and the largest mean, that's fully compensated by the numerical problems we are dealing with. So now we describe, and we are using in the following, gamma components. So that what's about the finite mixture of gammas. So gammas, of course, they are skewed components, so maybe they are more easily describing the first big heap in the histogram, because that was also somehow skewed. We are doing a parameterization because I'm coming from the GLM community, so to say, in terms of a mean. So that's the mean of the response being in the kth component, that's mu k, and that's the variance there, also the variance of a response from the kth component being some sort of a kth dispersion and the squared mean there. So what we need to do is to estimate the mean and to estimate the parameter, then we have all we need. Of course, we can also do it in the reparameterized version, and what we actually really did in order to guarantee that the dispersion parameter is strictly positive, we applied a log linear model for it. So the log of dispersion is a parameter. So this is something I can recommend, because this really is helpful in all the numerical iteration that goes on. So here's the result. After having done a lot of R programming, because we run into troubles because there was no package available doing the estimation for us that allows a weighting, such a prominent and necessary weighting. We did all the programming our own, and here's the result. So using the ICL, the integrated conditional likelihood criteria, it turns out that the 3-component result is the best one. Results in the lowest ICL criteria value. So you see there is a very first component here in red, with a mean here in this big red dot. second component here is in green. That's about 61% of all the data. And the second mean is very close to the first mean, and there is a long distance, nothing going on. And here, the third component. The third component has a mean of 190, and what we are interested in, as said, is the difference between 191 to 41. So this tells us the difference between the red and the blue value, how good the quality, how good the contrast is. What you also see here is the fraction of this blue component. The fraction of the blue component is a little bit less than 5%, so indicating that there are about 5% of all the wafer area is bond void area, is a situation which doesn't work at all technically. The problem here is, if the estimate of the third component is large one, if the estimated mean is large, so is the variance, or better to say the standard deviation, because you see the third component has to somehow account for all the grayscale values which are not green and not red. So that's the reason why it starts already here, has something like a mean over there, and further on continues to the far right. So this is something we should keep in mind. That's not very good news. So what I'm doing next is to recolor my first image of the histogram. What I'm using to recolor is the posterior, the maximum posterior probability here. For example, each of the row represents a grayscale, and you see the belonging, the component such a grayscale belongs to is maximum in if the index is the first one, or the index is the second one, or the index is the third one. So what I mean is, I'm taking a grayscale and I look which of the WIs are maximum, and I'm taking the occurrence of the maximum in as a, so to say, a color index, and I'm using red for the first one, green for the second one, and blue for the third one. So here you see switching from a 256 grayscale image over to a 3-component, to a 3-color image. And what you see is dark blue is actually really indicating the bond void area. So that's the largest component. And there is something like green and red being describing a structure, and that's exactly the structure of the little tiny chips on the wafer. And there is something more which I was shocked when I've seen it for the first time. Here on the left, it's not that easy to recognize. It's some sort of a horseshoe, and the horseshoe is actually a platform where the wafer is put down when producing the image. And the horseshoe has an impact on our acoustic signal. So what you see here is that it's much easier to recognize the horseshoe using a 3-component mixture than it was using the original data. Anyway, the green and the red is somehow taking over the role of a well-performing image or well-performing wafer area. It's the blue part which we are not happy with, and the more blue regions there are on a wafer, the less is the quality, so to say, of the wafer. So here is what we worked, what we get when the contrast was weak. So that's about image B. What you see here is the blue dot here is much closer to the red one. So the distance between red and blue is much smaller than it was previously. Maybe you also can see that the blue dot here is not exactly in the center of the small heap. It's some sort of being more to the right, so a little bit larger than we would expect its value. And the reason simply is that there are actually many observations here which are forming a very low fraction, but still it's less, or it's many out of 22 millions, but it can be recognized directly by watching this image here. So that's the weak contrast situation. And again, we see the blue dots here exactly reflects our bond void areas in the original wafer image. So we are happy with these three components. Also here it's very clear to recognize the horseshoe area and the center point, if you like to say so. So I told you that it's not only 2 images, we do have 133 images, and we are using now the model and apply the model to all these 133 images, and we end up with the following results. So from each analysis, from each estimated model, we take the estimated third component's mean in distance to the estimated first component mean, where we call it d hat, so that's the distance, and the distance, if the distance is large, the contrast quality is good. So here in the upper part, here are the good quality images, in the lower part there are the less quality images or less good quality images. And the color we used is the rating of the experts. So the experts rated all these images as being of good quality and all those one as being bad or of medium quality. So our model was not able to distinguish between medium and bad quality, but it was perfectly possible to distinguish between good quality and not good quality. So that's about this direction. The second one is about the quality of the wafer. So that was the quality of the image. Now it's about the quality of the wafer, and you see it's between something like 2% up to 5%. There is one outlier, one really extreme bad wafer of area in this wafer that cannot be used. So it's not good news for the producing institution to see that about 3% or even 4% of all the wafer area is not usable in practice. So here is an idea of how to improve what we found. So the average of pi3 hat, so that's indicating the fraction of bond voids, is about 3%. And the standard deviation of the largest component, which is in that setting the third component, is also very large. It's about 25, because that has to account this third component onto all the data which are not contained in the first two components. And sometimes the estimate of the third mean is really biased. I can show you that here. This is a different data situation. You see the red and the green are very nicely reflecting this first bump here, the major part of the grayscale histogram. And there is long time nothing, and here's the second little heap, but the estimated center, the estimated mean, is far outside the heap, so it's really downward biased. And this line here with the three colors, red and green and blue, indicates the regions of the grayscale values that belongs to the first group, that's the red one, or most likely belongs to the green one, or most likely belongs to the blue one, so the largest one. And you see it starts here, a grayscale of a little bit more than 80 already belongs to this group, and that's the reason why there is a bias in the estimation. And what we could do is, for example, to think to modify the model. So what I'm doing here is I'm providing you with the original histogram, and now I'm zooming in, and remember that's 500,000, that's 500,000 here. And now after zooming in, we do have something like a 5,000 there, so it's 1 to 100 rescaling. And you see there's a lot going on here as some sort of a base component. And what I'm doing now is to allow, in addition to the finite mixture here, also a uniform component. So what we are doing now in what follows is to switch over from a homogeneous mixture to a heterogeneous mixture, and that's the name Corretto and Henning were using when mixing gammas with uniforms, for example. So the formula is technically absolutely the same. So the component, the ith observation has now a density that is with probability p naught from a uniform, plus with probability pi 1, pi 2, pi 3, and so forth from a gamma, for example. So this is exactly an extension, a generalization using the same gamma mixture we had previously and adding a fourth or another component, and this baseline layer, this baseline component is in this setting described by uniform density, and the parameters are here called theta node or pi node. Of course, the uniform has a parameter that is describing the beginning and the end of the interval. So it's a uniform on the interval A to B. A, of course, has to be smaller than B. And now the sum of all these pi's has to be equal to 1. And here is the objective function in the EM, where this is an additional term to the mixture we had previously. So you see here that maximization of this Q is actually the same as maximization of Q was previously, with one exaction, that's the maximization with respect to theta node. So we do not have to take care of what need to be done in order to find updated parameter values of theta here or pi there. We only have to take care of what has to be done with this theta node parameter, and that's very easy to check out. First, let's describe what's U about with theta node. It's an indicator, so it's the value of 1 if the grayscale is out of the interval A to B, scaled by the interval length. This is the posterior probability with respect to the base uniform component. So all what we had previously is now this U here in this extended mixture we had. So what's the maximization doing with the boundaries with A and B? And what can be seen very straightforwardly is if you start with an A node as an initialization of the left and the B node as an initialization of the right bound of the uniform. So the first and all the following updates, they are actually the same values, namely take the smallest, in our situation, take the smallest grayscale that is at least as large as A. So this is the smallest observation we do have, and that's the largest observation we do have that is still at most B. So shrinking AB, starting to a tiny little bit inside, just that this is an observed value, and also the other side is an observed value. So here we see, or here we remember what we had previously, where I explained that there is some biased estimation going on. So what's going on if we add to 3 gammas another uniform, then you see we are really happy. So the third component now is exactly in the center of this little heap. So also the very first components, they do not change a lot. Let's go back and forth. And you see the red and the green situation, the 2 components are almost the same. At least they are very similar. So what we have now is this component membership. It's the red, the green, and the red part, as we had previously. Look at that one here. But instead of the third component already starting here at 80 something, our third component starts here at about 230 onwards. In between is now a black component, and this black component is exactly the uniform component we have introduced in. So by allowing a uniform component, we improve the model fit, and we get more realistic, more unbiased estimators. And so the results also should be more usable. The usability of the results should be higher. So it seems that the drawbacks are really resolved. There happened something, namely that the average of all these third component probabilities, they really reduced from 3.1% to 2.3%, which makes AMS very, very happy. We also see that the standard deviation of the largest component shrinked from 25 down to 9, something like that. And the mean of the third component, the estimated mean, seems to be less biased. So that was one way to use mixture models and to deal with mixture models, to play around with it. Here is the final graph of our 133 image analysis, so to say. We see it's the same scale we had previously, but now all these dots are smaller. They are more to the left as they have been to the right previously. And even to distinguish green to the red and yellow situation is, in my opinion, a little bit more clear as it was previously. So these greens are far higher. They are producing a far longer distance between the third and the first component, as this happened to be the case previously. So that's one way to improve the analysis by switching or not forgetting, so to say, that there is the possibility to also use a heterogeneous situation. Here's a second application. The second application is about regression, and that was quite a lot of programming effort necessary, not done by me. I'm absolutely not an expert in doing R programming, but having done by a PhD student of mine. That's about gas flows, daily gas flows in a gas network. And we are using network data from Austria. And you have to imagine that a gas network consists of storages, consists of entries where gas is pumped into, exits, where a village, for example, receives gas for heating, or some consumers generally, not only houses, they need gas to do some industrial thing and so forth. And what the provider of a gas network is obliged to do is they have to guarantee that there is all the time sufficiently much gas available at an exit. So they need to know how much gas is required on a certain specific day at its maximum. So we are actually dealing with maximum daily gas flows. So this is something I said already. We started with hourly data of gas flows, but we changed hourly into the maximum gas flow within an hour on a specific day. We do have data over several years. And because we thought, and that's really a good idea, that most of the consumption is connected with a heating system, we thought it's a good idea to relate the gas consumption to daily temperatures there. So we are using as a response now the daily maximum flow on day I for many, many observations. So usually this N is far more than a couple of thousand. So it's over many, many years. It really depends where the data are from. The data, by the way, it's an open database, so it's really available for anyone who is interested to work with that. So here you see very typical situations. It's data set 1. It seems to be something like a sigmoid functional decrease depending on temperature. So whenever the mean daily temperature is increasing or is large, then the consumption seems to be low. Whenever the temperature is getting colder and colder, the consumption seems to get larger and larger. So since the network company is obliged to guarantee that there is sufficiently much gas available at any exit, they need to have some information how much at the maximum is necessary when it's really cold. Possibly you can't see that, that's -9. That's for someone in Brazil impossible to imagine, but sometimes you see it also occurs in Central Europe. And here is the maximum, which is also very moderate. It's 26 degrees. That's a daily mean temperature situation. So this is a very homogeneous situation. That one is something different. It's no longer that homogeneous. There seems to be, look at that one here, one baseline consumption level and another baseline consumption level. So I thought this might be a situation where two different nonlinear regression models are somehow overlaying. This seems to be an observation situation of a mixture of two such components, and each of the components seems to follow a nonlinear regression model. So here it's not that clear, but you can also say that maybe that one here is a first component, also a sigmoid function here, and maybe over there is a second sigmoid function. So we need something like a model that accounts for this heterogeneity by its own. So we need a model that allows mixing generalized nonlinear regression models. Why are we talking about generalized nonlinear regression models and not any? Because we are dealing with maximum values. So when publishing that 10 years ago for the first time, I really had troubles because I was then only possible for me to use mixtures of Gaussians. We didn't have the software those days, and it's very hard to say that an observed maximum is from a normal distribution. So that, for that reason, we changed from a normal family to the exponential family as usual in the GLM context. So here's something I told you already. The gas operators, they are really obliged to sustain the supply of gas on also very cold days. So there is a definition that's called the design temperature, and the design temperature can be different in different regions, in different areas of the country. Usually it's something between -12 and -16. So think about having a mean daily temperature which is colder than -12. That's really cold. And yeah, it's really a pity that we don't have that many data exactly being observed at such cold situations. So what we could do is to borrow information or to borrow something like ideas on the expected maximum gas flow at such cold days by using a statistical model and by doing some sort of prediction based on such a statistical model. So here's the setup without any mixing components. So this is simply called a generalized nonlinear model. So as usually, we do have a mean. The mean is called mu. That's the mean of the ith response. And the mean of the ith response is a function, well-defined, known, so to say, of x and beta, not necessarily linear. We are dealing with a nonlinear situation. So x is a vector of explanatory variables. In our situation, x will only be the mean temperature on the ith day. So this h here needs to describe a sigmoid functional decay, and there are parameters. I will show you a model that we used to describe the situation very, very soon. So beta is the unknown parameters in the mean part, and there is a dispersion parameter being allowed for, again, think about using gamma distribution to model the maximum values. So this phi is a dispersion thing, and there's a variance function that depends on the mean. For example, in the gamma setting, there's a phi times mu squared. And since we do have a nonlinearity component here, nonlinear component there, it's, if you think about having a GLM and having to iterate by applying the iterative weighted least square algorithm, there is a inner iteration required, and this inner iteration is required by maximizing with respect to the parameter beta. So this is no longer linear. So here we go. Use this model in and mix away it. So that's assumed that all the components are stochastically independent. Here is the mixture of capital K such structures. So in each component, there is the same model family, the same model formula, but that model is based on component-specific parameter situation and on component-specific dispersion. So what we are doing now is to say, put all the pi's together in a vector pi, to all the betas into a beta, all the phi's, and so forth. So this is only about notation. And do not forget that we are working with a linear exponential family. So the variance of the response being in the kth component is equal to a dispersion parameter times a variance function there. So now put all the parameters that are defined in our system together, and let's try to estimate this big, long parameter vector, again by applying the EM. So this is nothing more. We also define the posterior weights. So we do have here the mean structures. In the E step, we are calculating the Q function, and in the following M step, we are maximizing the Q function as we did it previously. There's a lot of numerical details to be accounted for, and programming sometimes is not very easy. You need some sort of tricks in order to keep going on the iteration till convergence. But finally, you end up with the maximum likelihood estimator, and that's good news. So what about the number of components? Of course, if you increase this value k, that has an impact on the complexity of the marginal distribution. So what could be done, for example, is to graphically explore what the data are about, or to use any criteria. For example, what we did is to use the ICL, the Integrated Classification Likelihood Criterion, which is very, very close to the AIC, but instead of using the log likelihood, we are using the maximized objective function in the EM algorithm. So Q at phi hat, plus how many parameters are there in the model and the log of the number of observations in our sample. So here is the sigmoid function. We use either normal or gamma components, and we model the mean as beta 4. So this is the low asymptote, so to say, plus beta 1 minus beta 4. So beta 1 is the upper asymptote. So we do have an upper and a lower one, and in between there is a decrease going on. And we are using this beta 2 and beta 3 parameters in order to describe the shape of the decrease. We are centering the temperature by shifting it by 40 degrees down. This is really helpful in stabilizing the iteration. Anyway, what you see here is the second gas data set without any model being applied to, and here what the model, a two-component model, a two-component gamma model results into. And we, using gamma components, we see really that there are identified two distinct gamma components, and these two distinct gamma components, they do have distinct minima. So it seems that there are on one hand days where this is describing the maximum gas flow need, and other type of days, whatever the type of days really are, where this is the correct, or this is the better model describing what is the maximum gas flow needed on that. And what we see is the colder it is, the larger the needed gas, the maximum needed gas becomes this value. So here's a rootogram that simply says how well is the separation going on. So is it component 1 or is it component day? And we are counting how many of our data belongs, oh, I should put it over there, belongs to component 1. Here is the probability 1, or it's large. So those are all the days belonging to component 1. These are all the days belonging to component 2. So the more clear this rootogram would be, the more clear would be the separation of any data into the first or the second group. So I show you now the gas flow 3 situation, and as expected, it's not only a very heterogeneous situation going on. No, it's a compound of two different models. So it's the red model and the blue model. So we are mixing these two situations, and you clearly see that these points here are the larger one. They forms a nonlinear model, that one here, and this seems to be more or less simply a shifted version of the other one. So that blue seems to be the red one, shifted by, for any of the mean temperatures, by almost the same amount. And what can be also nicely seen here is, look at this red component, that the variability, as when the mean is large, the variability is large, and this variability shrinks down whenever the mean becomes smaller. So it really seems, by simply watching this behavior, that a gamma assumption seems to be appropriate one. So here's the rootogram. Very, very nice, very strong separation. So component 1 is clearly separated to component 2. So you see those guys belong to component 1 and these guys here belong to component 2. It's very well separated. So I think let's come to the conclusions, and sorry for being late, for being that stupid without having the chance to start in time. So my message here is, especially as the second example is considered that a mixture of GNMs, which I've introduced, accounts or is able to account for heterogeneity in the data whenever the data follows a model that is nonlinear in any explanatory variables. What you have seen is available in R. There is an R package, the very famous R package developed by Bettina Grün and Fritz Leisch. That package is called FlexMix. And on CRAN, we've put now an extension called FlexMix NL. So this really only accounts on what has to be done in addition to what already is available in FlexMix. So whenever you do something mixing something nonlinear, you can base your analysis on aspects that are already available. And those aspects are, for example, model estimation, diagnostics, or even visualization techniques, all done already by Bettina. So at the moment, it's for Gaussian and gamma mixtures implemented, not for any discrete situations, and we are very proud of that. Usually it's some sort of a drawback when working with the EM that we do not automatically end up with standard errors or variance covariance matrix. So what we are doing here in addition is we are calculating standard errors based on the marginal Fisher information, and that is something that is additionally provided. So I think that's a good point to stop here. The next two slides are only on selected references for the first, and for the second application, I think it's good to stop here. Thank you very much.
Thank you very much, Erwig. It was a great talk, very enlightening. It is a pity that we cannot applaud, but you can feel it.
I got the message.
I don't know if anyone has any question. While people think I have a question myself, I was wondering whether you had the chance or you plan to compare with some other classification methods. Like in the last example that you gave, I thought about support vector machines, for instance, that could make I don't know, a distinction between the two groups. I was wondering about that.
No, my honest, true answer is no, I didn't, because I'm not that familiar with all these modern data science technologies. I'm more familiar with the old traditional statistician technologies that can be applied for such data. Actually, no, but it would be really nice. Thank you very much for the hint. I should do that just in order to figure out how much better or how much worse is one model or one scenario compared with the other one. Thank you very much for pointing to that.
Yeah, you are welcome. I don't know if anyone has any further questions. I don't think we don't have any question on YouTube. I don't know if anyone in the room has a question. Clarice, please.
Here we go. Thanks for this very interesting talk. It was really great to see your explanation. I was wondering if you have tried to identify. Can you hear me?
Yeah, I can hear. Yeah. I think I already got what you'd like to ask me. Is it about the second example?
Yeah,
the gas consumption.
Could be any.
Okay. In the second example, it's really nice. The idea I had was that one component somehow accounts for working days, and the other component accounts for holidays, because usually during holiday season, people are not at home, and for that reason, there is no need for the heating system. But the point is, that's partially true. It's really, if you introduce an additional holiday indicator, so to say, this is something that is significantly different from zero. So I showed you a model that is much too much primitive as it should be. But the message was, show it as easy as possible in order that you show the main message. But I go fully with you. The problem is, even after having introduced an indicator accounting for working day or holiday, it's still a two-component approach. So the model becomes better, it becomes clearer, but there is still something like unobserved heterogeneity going on, which we don't have an idea the reason why it's there. But thank you very much for pointing to that. I fully forgot that we tried the usage of such an indicator, and it was a success, but it didn't solve all these heterogeneity issues. It was still the need for a second component there in the gas situation, in the maximum gas consumption situation.
Yeah.
Thank you very much, Clarice.
Thank you very much.
Thank you very much, Erwin. Thanks, Clarice. I think we are on time. We can close now. I'd like to thank again Eric for his nice talk, and also Geert. So now we will be back at 2 p.m. And it will be with a talk by Rafael Moral. He will be talking about estimating animal abundance when data is scarce. So thank you everyone for being here. Obrigado a todos por participarem. Voltamos às 2 com a palestra do Rafael. Thank you very much.
Thank you very much for having me.
Thank you. Bye-bye. I see you later.